anybody.
Yeah, I'm not ready 25.
I mean, okay, we had some beer yesterday with the speakers, with the lecturers, so they claimed they could handle it. Like the height and stuff. But I don't know, we should look at the cards. Start. Oh. Oh, and you can still zoom properly.
Yeah, I can zoom properly.
Yeah.
And just proceed.
Okay. Yeah.
And just proceed.
I mean, that will be better. Right. And you put
Money.
carefully this. So you look at all the probably wait a few minutes for in case there is, I know, any more discussion.
I suppose it depends on the severity of the food poisoning. It's done.
And it depends on last night's thing.
Yeah, like they went back to the same restaurant. With, controlled experiment. No, but no, they were that version. So you can do semi-road and some other versions.
Oh, I see, okay.
WC, solutions.
Sorry, I think that,
So we are going to.
Recipe.
Oh, okay. Right, space not digital. So this can work inside.
Other bits, people coming in.
When you use the car, you go to these sections, you see parking. But don't do that.
Seems to work.
So, yeah. Yeah, I mean, the road floor, but, how we go it, and station management, for the rest of the building. I've lectured there. So, how to do it. But the ground floor and the but it's not the main, the big building is the one who's ownership. But the building is to the left. And people. At the corner of the house. I don't see it. No, this was before, this was when I first came.
We are not in campus.
Oh,
No, actually, so I sent him a message and it didn't go through. So when he's in campus, it's
Ah.
not taken.
so we probably can start. Yeah. Okay, we did that, we did that one.
First broke.
Okay, let me just, give me 1 second. I'm still confirming that. All right, so I think we can get going with the third day of the school with Sam continuing the video fourth lecture. One announcement is that I think maybe after the coffee break, we'll take a picture just here, just before we start the next lecture. Have cameras.
Okay. Okay, so yeah, so yesterday we looked at a few examples of math equals for the harmonic oscillator and the fermionic oscillator, which can be computed exactly and matched with the Greenwald prediction functions. So today we're going to extend that computation to a generic supersymmetric quantum mechanical system. Okay, so to do that, let me first write down the action for this for the system that we considered. So that's related to that's the Lagrangian associated to the Hamiltonian we saw before. So it's given unsurprisingly by this function h x. And then that's the bosonic part. And then we have kinetic terms, the fermions. I'm splitting up the kinetic term using a partial integration for later convenience. But these just add together to partially integrate this, so you add together, we'll just get an ordinary kinetic term for fermions. And then there's the second derivative term, which couples x to the psi variables. And here every variable depends on time. X and psi dagger and psi are all functions of time. Okay. So the claim is that this is a supersymmetric action. So what does that mean? Well, we've seen yesterday's lecture that by Mayer, he sketched the general form of supersymmetry transformations. But let me make let's do that explicitly here. So give some. We're going to look at this general story in the context of this quantum mechanical system. So the variation of the bosonic variable will be given following expression. So they psi. So x. So the symmetry transformation relates x to the fermionic variables, and there is an associated Grassmann valued symmetry parameter. But, I think you also call them epsilon, right? Yes. It's the same epsilon. So this is a Grassmann valued and variations of the fermions instead relate to the Bosnian variable. Okay, so the claim is that the action is invariant under these transformations. So I'm not gonna show that explicitly, leave that as an exercise, but spell it out a bit more. So you can show, the exercise would be to show that the variation of the action under this transformation is given, it's given by a total derivative. Yes. So this is a good exercise. Try to figure out. And the fact that it's nicely symmetric in epsilon and epsilon dagger is because we choose this kind of term in this way. Okay. Now what we also have seen, also mentioned in Maria's lecture, was that two supersymmetric transformations square into a space-time translation, remember. So what is that in this one-dimensional system will be expected to go into the time translation. So two supersymmetries should combine into the time translation. So let's check that a little bit more explicitly. Let's compute the following things. Sorry. Sorry, let me. Yeah, maybe it makes more sense to first extend this slightly to compute the negative charges associated with the symmetry. Why did I use this? So, okay, so let's first compute the negative charges associated with the symmetry to show that that connects with the Hamiltonian formation we saw before. So how do you compute the negative charges associated to the symmetry transformations like this? There's this trick that you make the symmetry parameter local, make it depend on time, and then the statement of negative state is that the variation under this time-dependent symmetry transformations of the action gives you, if you write it in ways, you write it as collecting what multiplies time derivatives of epsilon and time derivatives of epsilon dagger gives you the charges. The charges Q and dagger. So this exercise is not that tricky to do if we've already done this, because we can do two partial integrations here. And in addition, we will get some additional terms from the variations of the kinetic terms when we make the epsilon parameter dependent on time. What you'll find is that
how do we know that those are the supersymmetric charges, right?
that will be the negative charges associated with these symmetry.
And these are not the same as supersymmetric charges.
We will see that we'll see that upon quantization, there will be the supercharges that we saw. So, you just, so you can view this as part of the exercise. So we now do this more general transformation where epsilon and epsilon dagger depend on time. We do a partial integration of that, we combine that with the additional terms from the kinetic terms, and you'll find that delta S can be written in this way. Minus I epsilon dot dagger I x dot plus the h prime of x. Minus I epsilon dot dagger psi minus I x. Okay, and if you compare these expressions with what we used in the Hamiltonian formalism, you'll recognize that these are precisely Q and Q dagger. To go to the Hamiltonian formalism, you have to first replace x dot by p, and then promote everything to operators. You get the expressions between people. So that is a nice exercise to combine with these. Okay, so then let's get to what I was saying before. So let's see that two of these supersymmetry transformations indeed combine into a bosonic transformation, a time translation. Let's do that. Be more specific. So if you compute the commutator of a delta 1 and a delta 2, where 1 and 2 refer to some parameter epsilon 1 and epsilon 2. If we act on this with these guys on x, and just plug that thing in, we get the following. So we get we have first have delta 2, we're acting on x and then delta 1. So we get an epsilon 2 of delta. Dagger minus epsilon 2 dagger delta 1 psi minus the opposite minus epsilon 1 delta 2 psi dagger minus epsilon 1 dagger psi. Right. If you plug that in, you can now plug in the delta 1 and delta 2 by using, in addition, these transformations. And what you'll find is that it's written in the following way. So we can minus x dot x minus epsilon 2 epsilon 1 pi instead of x, and now minus the term with epsilon 1s and epsilon 2s exchange, and the vectors. Right. And then various things cancel, and what you end up with is indeed a time translation of excellent. Right. You indeed see that there's some parameter here. Let's call it alpha. And we see that the supersymmetry transformations, the commutator of the supersymmetry transformations gives rise to a time derivative of x. And that's that's the Lagrangian way of thinking about this Hamiltonian commutator to H. Right? Okay, you can do this a similar exercise for the fermion. Okay, and what you'll find is that again you can express it entirely the same way, except for the fact that you have to use the equations of motion. So it squares for the fermion, they square to the translation up to the equations of motion. Okay. But it's sort of the same. Correct. And similarly for the group side. Okay. Any questions about that? Okay, so it would in higher dimensions, and that's also what Maya showed us. So Maya showed us something like for Maya it would be alpha mu, where P mu is the generator of time space time translations. But in our case, there's only time, right? So in particular, also Maya was talking about gamma or sigma matrices. And those appear when you multiply spinors like these together to contract the indices, but in one dimension, the spinors are just one dimension. So there's no indices. But indeed, so this is an illustration of captures most things of the general story. There are just some in higher dimensions, you get more bells and whistles associated with the representations of the words. But that's about it. The structure is essentially okay. Well, any further questions? Okay, then we're basically set to compute the difference. So let's see. So what we said is that we can compute I as follows. So it's a path integral over all the fields in the theory, where we impose, or we always impose periodic boundary conditions on the boson, but for the Witten index, we also impose periodic boundary conditions on the science. We would choose anti-periodic boundary conditions, which is a route for fermions to compute the thermal condition. Periodic boundary conditions give the Witten index. Now you can also notice that we have a different perspective on why periodic boundary conditions compute supersymmetric observable. Because the supersymmetry transformations, they relate the bosonic variable to the fermionic variables, right? So the left-hand side here is a periodic variable. So this transformation would be inconsistent with the right-hand side being anti-periodic. So that's a different way of understanding why this is indeed the right boundary condition for the index. Okay. Yeah, with Euclid, as usual with Euclideanites, we've done with rotations, we get minus the Euclidean action that we read about minus 0 to beta tau Now there will be various plus signs appearing instead of negative sign in parentheses. So we're asked to compute this path integral, but this is very different from the path integrals that we saw yesterday. Yesterday we looked at quadratic actions, which we can compute explicitly. But in the mode expansions, diagonalize everything and compute the determinant of the output. But in this case, there will be, we're allowing H to be a generic polynomial, or even a generic real function. And then this normally only compute this path integrals some perturbative approximation. But it turns out that these boundary conditions allow us to compute this thing exactly. Okay? So that's quite special. And that's also, I guess, one of the main motivations for that I mentioned all the way in the first lecture, why symmetry is interesting for theoretical physicists, because it allows to make sense of this path integral exactly for non-quadratic actions. Okay. So we'll do two computations that are essentially related. The first one is we're going to use a very similar argument as in the Hamiltonian computation. So in particular, we'll use this argument that this guy is invariant, or we will show that this index is invariant under this scale, which implies that the path integral ultimately just reduces to a quadratic action. So that's very similar to the Hamiltonian, but the way to show that the path integrals any kind of such scaling is a bit different. So that's why I'll still discuss it. And it's also a typical argument that appears also across various dimensions in QFT for higher dimensional QFTs to argue with for the compute or to compute these symmetric path integrals. So it's useful to see. But then the second computation I think is a bit more novel, and that is what's known as. They're not completely distinct, but this one is more clearly related to this notion of localization principle. It's a somewhat more abstract argument, which will lead us to conclude that only a very small subspace of this functional integral contributes to the path. So we basically can reduce this functional integral to one. That means we'll do both of these arguments because they're both useful.
Just going back to what you were saying about the periodicity conditions on the fermions. So if we want to calculate the partition function instead of the Witten index, we can actually use the path integral formulation to do that, because the supersymmetry would be broken by the.
So supersymmetry is broken. Well, yeah. So but you could still try to compute it, but then you just encounter all the difficulties that you encounter with non-functional integrals. And it's a well-defined integral. Well, I shouldn't say well-defined. But For physicists, that's the typical integral that we write down, but you just don't have these two arguments. As we will see, both these arguments rely crucially on the fact that this action is invariant.
So you can still calculate the partition function in that way, but you lose like the technology of the
Yeah, so you lose both these arguments, so you don't have the argument of invariance in your scaling, you don't have the linearization principle, but you can still try to compute it using perturbative techniques, but you will not be able to do it exactly, because nobody can compute any integral more difficult than the Gaussian. Exactly. Okay, so we start with the first argument, which is this, ultimately quite similar to the Hamiltonian thing. We're going to imagine to rescale the potential by some large number. And then we want to show that di lambda, or we can show that the I d lambda is equal to 0, then we can take lambda to infinity, which will make the quadratic approximation to the mathematical exact. So let's compute this. So di lambda, the action here, we compute the I lambda, we have a lambda squared appearing here and a single lambda here, so what we get down, single lambda here, so what we get down, after the growth, I'm just known generically fields, after the growth of all the fields. And then what we bring down is the following. Bring down minus tau. Lambda, single power of lambda h prime squared. And then plus h double prime x side to side. And then just the action. Right. Okay, now a crucial observation is that this object can be written as a total supersymmetry transformation. So the first step that I'm going to show is that if we multiply this by epsilon plus epsilon negative times this term, that this is equal to a modified supersymmetry transformation without living by lambda. Let's explain now. This is a supersymmetry transformation following thing. So h times psi plus delta lambda is just our original supersymmetry transformation, but with the rescaled version of H. Okay. We're first going to show this. Well, this is not too difficult to show. You just work that out. You can find that delta lambda of H prime psi plus psi vector. This is equal to H double prime of x. We first have delta acting on H prime, that is H double prime times delta lambda of x times psi plus psi dagger plus use the H prime alone and act on both psi and psi dagger. Okay, is that clear? And well, using some algebra, you'll find that this can be written as epsilon plus epsilon dagger times lambda h prime squared plus h double prime psi dagger psi. So that's essentially what we wanted to show. There's one additional term, this proportion to epsilon dagger minus epsilon, which is h prime of x dot. Okay? But now, remember that we're interested in the tau integral of this thing. And I've written a circle for this, but it's really from 0 to beta, but all functions are periodic from 0 to beta. And this is nothing but a total, derivative. So the 0 beta integral of h prime x dot is nothing but 0 to beta dh. Sorry, I should put the tau here, of course. Right? This is just 0 to beta of dh. The h is a periodic function because it's a function of a periodic function. So with period beta, so this is vanishing. So the tau integral of this thing indeed gives us our statement here. So that what we have brought down can be viewed as a total super. Well, if we multiply by epsilon plus epsilon dagger, can be viewed as a total supersymmetry transformation. Okay, but that's important. So how are we going to use that? We need to observe one more thing. Observe one more thing. Namely, we can express these variations in terms of functional derivatives. Okay, so we can do not confuse these q's with the charges that we computed earlier. These q's are closely related, but these will be functional derivatives. So let's understand why this can be done. So the claim is that we can view this variation in this particular way where Q, so I should label them by lambda, just to indicate that all of these variations are with respect to the rescale potential. Q of lambda can be written as tau integral of psi dagger tau delta x of tau. This is a functional derivative with respect to x. And then plus minus x dot. That's the difference. Lambda x times delta psi. And the dagger lambda is very similar to tau minus psi tau x plus x dot that's so why is this so? Well, we can just, so first of all, maybe just to remind you that functional derivative x with respect to x is equal to the delta here, delta functions. Don't mistake these deltas and spell. Similarly for fermions, that's what a functional derivative is. You can just check. It's not difficult to check, but if you take delta lambda in this way and plug in these functional derivatives and have them act on x, so epsilon 2 and epsilon derivative, and on x. But this precisely gives you these transformations that we mentioned. Okay? You get some Dirac delta functions, but that's why the integral is included that gets rid of it. It's equal to the delta side. Is that clear, or should I work out this example slightly more? Let's do it. So we get epsilon. Now we act with this guy on x, right, which gives us a sine Decker of, this will be x of tau prime. We get a sine Decker of tau. We get a delta function of tau prime minus tau, but there's still the integral here. So that just gives the psi Decker. And similarly for the second term. Okay. And the same goes for the first. Okay, so we can write this symmetric transformation in terms of these functional derivatives. Yeah, and what is more, we have that. What we also have is that we already showed that the variation of the action is 0, right? And this implies that Q dagger lambda acting as 0. So Q dagger lambda minus. Okay, so what does this mean? Just because we know that here this delta lambda of h prime psi plus psi dagger is epsilon plus epsilon dagger times this object. We can now write the derivative of the index with respect to lambda in the following way. We have still the functional derivative over all the fields. And then we have this Q lambda plus dagger lambda acting on h prime of x psi plus psi dagger the exponential minus the action. So this is an equivalent. This is the expression for the thing we brought down with the derivative of lambda. Especially as an action of q dagger on this function. But because the action of q and q dagger on leaves as e invariant, I can actually extend this to include the entire interval. That follows from the fact that the s is invariant under this case as well. So what we now have is that we've expressed the derivative of the index with respect to lambda as a total derivative in a functional sense of some function. Okay. And now the claim is that that evaluates to 0. So maybe in slightly more detail, similar to how a total derivative of an ordinary function, of an ordinary function, so total derivative in an ordinary integral evaluates to 0 if the boundary behaves. So let's just look in a little bit more detail at that. So for the fermionic part, so there are both functional derivatives for the fermions and for the bosons. For the fermionic part, this is 0 function. This total derivative is 0 follows essentially from Grassmann integration. So we can express part of the fermionic part of the functional integral in this way. So we just focus on the fermionic parts here. On this whole thing. And this vanishes by the usual rules of Grassmann integration, because in both cases I take whatever is here, I take out a psi or a psi dagger, then I integrate it again with respect to psi and psi dagger. And integration in Grassmann variables is the same as the derivation, the double derivation is 0. So this fermionic part of the total derivative vanishes from Grassmann integration. Now the bosonic part is really is like be expressed in this way. And the idea is that so we have to the idea is that this functional integral then becomes the evaluation of whatever is here in the boundary of field space. So the idea here is that e to the minus s e x goes to 0 for let's say large values of x. Which is sort of reasonably, which can be viewed as sort of the boundary of the field space. There's a little bit, there's not complete rigor here, but this is the idea. So this also evaluates. So this goes to 0. So that means that this is equal to 0. Okay. So that is our path integral way, which is quite different, but our path integral way of showing that the index is independent. So then, as I already said, then we can compute it at lambda. Then we can conveniently set lambda to infinity. The potential becomes very steep. That means that fluctuations become very localized around the minimum potential, and the quadratic approximation becomes better and better, and at lambda infinity it becomes better. So we can just do the quadratic approximation of the action. So function, which is also called S1 loop. The action then becomes tau dx tau squared. And then similarly to the Hamiltonian computation, we sit close to a critical point of h, where h prime is 0 and expand there, you get h double prime squared minus the critical point squared. We still have the fermions kinetic term will be also expanded. Here, that's x is xi. Psi. So this is the quadratic approximation of the action, but this we computed yesterday. So we computed separately the path integral for the harmonic oscillator where h double prime was xi. We called omega yesterday, right? And we also computed this thing, the fermions, where we call this guy omega. So we can just use the results now yesterday to say the path integral of exponent minus SE is given by the sum over all critical points. For each critical point, we have this same story. We have two fermionic and bosonic harmonic oscillator. And then remember that fermion determinants gave a cinch of beta omega over 2, omega now is h double prime xi. So that's the fermion. The boson determinant was very similar. It's also a cinch hyperbolic with 1 over the cinch hyperbolic. That's beta. It's also a cinch hyperbolic with 1 over the cinch hyperbolic. That's beta, an absolute value of h double prime xi over 2. Okay? These guys are almost equal. The only difference is that there's an absolute value here. But they almost cancel up to a minus sign eventually if h double is negative, because the cinch is antisymmetric, they got a minus sign. So this is nothing but the sum of the critical points of really the sign of h double prime evaluated at xi. Right. The sign just takes the values plus or minus, depending on the sign inside. So here, I think your question yesterday was how to reproduce these formulas for your path integral. So this is how it goes. Okay. But, so we said we're going to do it in two ways. So let me end today's lecture with the second way of computing this. Because you might think that, okay, we reduced the path integral to the quadratic. We reduced the path integral to the quadratic approximation by making use of this standardized scaling. But we're still doing a functional integral. So I haven't made true on my promise yet that for the index you should think of the path integrals in ordinary. Index you should think of the path integrals in ordinary. So that's the second way of computing the index. And the reason also for discussing this is because this story is very general. So this doesn't just apply to supersymmetric quantum mechanics. But this argument applies to all supersymmetric particles in any dimension Q of T. That's the organization. So yeah. So in particular, what we'll see is that here effectively you still have data dependent terms, but there's just a lot of cancellations happening. So we're going to avoid those cancellations altogether. Arrive at the independence of data a bit more explicitly. Yeah, so the claim is, I should start with the claim, is that the localization principle is the statement that the supersymmetric integral localizes we're generating this supersymmetric functional integral. It localizes on the zero locus of supersymmetry transformations. Okay, so on where the delta of the fields involved in your theory are all set to zero. Okay. So let's first give the general argument for why this should be true, and then see how the functional integral then reduces to an ordinary. So the general argument is that, let's say that we have some path integral, some space of functions, E is some action. Okay. Let's say that this theory has a symmetry that is generated by G. Okay, so there's some symmetry group G which acts on the fields of the theory, and the action is invariant under this action. This symmetry. Now, if G acts freely, so that it doesn't have fixed points, you can express this integral in the following way. You can just, so what it means for the symmetry is that two field configurations that contribute to the integral that are related by the action of G, and they give the same contribution. Right? So we can factor that out. We can say, let's only look at field configurations modulo this action for G, which is well defined because we're assuming that G acts freely. So, and we do this integral over this reduced space function space. And we just multiply by the volume of this integral. That's an equivalence expression. Okay. Now, in our case, we're not just dealing with an ordinary symmetry, but we're dealing with a fermionic symmetry. And the basic idea is that the volume of this fermionic symmetry is equal to zero. Okay. So if there's a fermionic symmetry that acts freely on the space of fields, then this would be zero. So sort of another way to understand that is that Okay, this fermionic symmetry, what does it do? It relates some bosonic field configuration that is in the particle. It relates it to a fermionic field configuration, which is parameterized by some Grassmann parameter times, schematically, the bosonic field configuration. So so we can think of the integration over the fields as an integration just over the bosonic field configurations, and then in addition, an integration of this Grassmann parameter. The statement of supersymmetry is that the action doesn't depend on this Grassmann parameter because it's the variant under this transformation. But if we integrate the Grassmann parameter, if we do the Grassmann integration of something that doesn't depend on the Grassmann parameter, that is like a derivative. Because it's like a derivation, it evaluates to zero. Okay. So what we claim here is that if we have a fermionic symmetry that acts freely on the space of fields, then the whole path integral is equal to zero. Okay? But the fermionic symmetry does not act freely. It does have fixed points. The fixed points are precisely given by the zeros of the supersymmetry variations. So, write down the symmetry transfer. So just based on the range again, you have epsilon. Working in Euclidean symmetry now. There's no I, which we cancel against the number. Okay. So the claim of this argument is that the path integral only gets contributions from the fixed points of the fermionic symmetry. And that's where these guys are equal to zero. And that is the localization principle. So these equations, so the equations where the variations of the fermions are equal to zero are also more generally known as the BTS equations. And this argument is very general, as you can see, and it goes for any supersymmetry on the field theory and associated problem. And so, of course, the details of these BTS equations will depend on the theory of the dimension. And so, of course, the details of these BTS equations will depend on the theory of the dimension which you are. But the key point of all these supersymmetry parameterization papers is to essentially solve the BTS equations and then compute the path integral around quadratic with compute the path integral with the approximation around these BTS configurations that solves these equations. That's the key thing in any localization. Okay, so that's the general story, but let's solve this in our case. So what are the solutions to these equations? Well, clearly we should just take psi equal to zero. That's a very generic thing. So the fermionic fields are set to zero in the BPS configuration. Now, in addition, we have to set these guys to zero. That's the less trivial part. And because there is a sign difference between these two, we have to take the term separately equal to zero. So we have to take x dot equal to zero and h prime x equal to zero. But we already know, so and by the way, these two equations also psi, psi dot is equal to 0. So the time derivatives of psi after fermionic field states. So these are solved. This is solved by x just being equal to its 0 mode. So remember the mode expansions of yesterday. We just take the constant part. That solves this equation. And this guy, so x has to be a constant. It actually has to be a more specific constant. It has to be a constant that solves this equation, which we call the x. So x0 equals with xi, xi the critical points of the potential of the function h. Okay, so then we can, the idea is that whole path integral reduces so we still consider small neighborhoods. We still have to consider radical fluctuations in the neighborhood around these points. But it's only with respect to the 0 modes that these fluctuations occur. So the functional integral reduces to this ordinary integral of the action on the 0 modes loses all the kinetic terms. We expand it close to h double prime, close to x is xi, so we get remains is minus a half h double prime divided by xi squared, which is the 0 mode. Fluctuations in 0 mode. Minus h double prime xi over 0. This is just an ordinary. Also, I should say we still sign over the critical points. These are fluctuations of the 0 modes around each other. But this is an ordinary Gaussian integral. This is a finite dimensional, one-dimensional Gaussian integral, both the Gaussian and non-Gaussian parameters. So we can just get immediately now the absolute value of h prime is I. Again, the absolute value of this. Absolute value of h double prime because there's a square and a square root from the Gaussian integration. And so in this way of reducing the path integral, we avoided these functional determinants and just immediately localize into the 0 modes, which gives this finite dimensional. And then I think I can end here. Questions? Thanks.
So, very clear about the coefficient M1.
Yes.
This argument is like, then we probably get an appropriate range, right?
Well, this is a little bit sketchy. So first of all, this is a space of functions. If you would consider, you can. This argument also works for ordinary spaces and ordinary integrals. So if you're in, well, yeah, you can also consider this as an ordinary integral, but in this argument, it's not functional. It doesn't really matter. Yeah.
Yeah, there's a few that I don't
say again. And in the code, well, but yeah, this is it's like a quotient, rather. Yeah. So it's some subspace that the statement that the manifolds, so it's the usual picture people have, is that if this G acts freely, it relates points in some points in this space in some direction, and the quotient manifold would be this section. So we only figure a single representative of each space. This is the quotient. So let's call this M. This is some subspace of the big space M. So that's the picture we should have. Again, this is all in the functions. This is the G.
No more questions? Let's thank Sam again. And check out coffee next door, and maybe we can try to
It's a variation which gives you some yeah, you do two more shots.
I'm just trying to
Yeah, you do two more shots.
I'm just trying to
Oh, yeah, yes.
Yeah, but we are basically assuming that this will give us the symmetry of
No, we're showing it. So it gives you a purple derivative.
okay, this is the
Yeah, which then is going to change. Purple derivative.
okay, this is the
Yeah, which then is going to change.
yeah, on the potential side, there will be definition of idea. So yeah, on the potential side, there will be definition of idea. So
Yeah, I mean, it's you do this like to rely from it, I suppose. You propose some definition of the fields which satisfies corresponding conditions and whatever, and then you see what it does in action. It does these action variances.
and the reason why we can do this is that we can take epsilon inside. Like there are two terms here, right? And there is a dt outside, and this make it a total derivative. We need to take epsilon. Just say that epsilon is independent of it. And then what we'll get is epsilon, and then a total derivative of this thing, and the boundary condition of side ever, and for the boundary condition of side, right, which we get 0. So this is indeed a symmetry. But then we are assuming that epsilon is independent of time, and then whatever we got later on, because epsilon is dependent.
Yeah. What do you ask?
Then this is not really a symmetry of the action. Because in here to get this as a symmetry of action, we needed to assume epsilon was independent of time.
Yeah, it is independent of time.
Then when we get
This is a trick to calculate this is like a standard trick that you can do where if you can write it, so you take whatever your constant parameter of the symmetry transformation is, right? And you imagine that it depended on time. And then you do the symmetry transformation again, and you get something that will have the form. It of course, since this is 0, it's independent of time. Whatever you get by making it dependent on time must be proportional to the time derivative of the epsilon, right? Because it's precisely by making epsilon constant that this vanishes in that keyword, right? So this is a trick whereby you consider that it's independent of time, and it's just whatever thing multiplying it you get is then the charge. Yeah, and then he picks out the charges because it's whatever multiplying the derivative of the parameter that you made. But epsilon is in the actual symmetry transformation, epsilon is independent of time. This is just a trick to calculate the inertial charges. So normally you calculate the inertial charges in that whole other way, right? Whatever, all that stuff. This is just like a shortcut. And I mean, I can't remember exactly what the argument is for why the charges. Oh yeah, this is why. We want the inertial charges should be conserved, right? Yeah. And the way you see it's conserved is here you can integrate by parts, and you can shift the time derivative from epsilon onto q. And now you're back in the situation of a constant epsilon, which means q dot. Right. So that whole thing is just like it's just a calculation trick. Yeah. Dude, where I kind of zoned out a bit here. Where did this expression come from? So he solved the BPS equation. Yeah. Right? Yeah. Then he plugs in here, right? To our actual plug
I think that's he made an expansion, Taylor expansion. So it's like now you can, what he has shown is that in general your action may not be quadratic, right?
Yeah.
And here we are making a quadratic approximation, but the quadratic approximation is exact because of this lambda infinity thing. So he has done a Taylor expansion around xi. Taylor expansion of what? Let me see.
Must be because h prime vanishes, right?
Yeah. So where is the h?
Oh no, but h prime. Because okay, so the last term is what you put as here, right?
Yeah.
But then what is he Taylor expanding?
So h prime is 0, right?
This is 0, this is 0, this is 0.
No, the last one is not 0. The first one is 0.
Yeah, sorry, this and this is 0.
Second is also 0. H prime of x is 0. See?
Yeah.
It's written here.
Oh,
H prime of x is 0. On the third line, BPS equation, side dagger size 0, and just below that.
oh no, but x, yeah, no, I see that. But x, remember we're considering various, because he's,
Wait, it's clear that he is doing a Taylor expansion, right? If you can just figure out where h of x is, because that's the Taylor expansion of h of x. H of x itself, I think he's taking to be 0.
no, but it's not, because it's squared.
No.
This was a Taylor expansion, you would square it into the second derivative. But I agree that it seems like there's Taylor expansion happening somewhere, because he's getting,
So maybe it's like h prime of x, h double prime of x, and then it's multiplying with something, and then it's being Taylor expanded. So essentially, all of this may be coming from the last term, right? How do we get this psi dagger naught and psi naught? Because psi dagger and psi are supposed to be 0, no?
yeah, but that's the thing. So he's considering I think, so this just must be like a fluctuation contribution.
Yeah, that's what he said. It's a fluctuation contribution. That's why we are Taylor expanding. But Taylor expanding, how does it connect? That's what.
So, yeah, that's what but this
and the integral has also gone away. See, so he's taken, I think, the classical thing. So the integral over t has gone away now, right?
Yeah, so that. This probably is just the standard fluctuation.
So I think we can write this thing like this. We can write this thing like this. this thing can be written like I'm writing the inside the bracket mark, right? You can write this as h double prime of xi, and then Taylor expansion.
Yeah.
And plus, that will give this h double prime xi, and that would make this one square.
Yeah.
So is there a term that is proportional to this? There is a large term that's sort of like this, no? H double prime side other side. And this could be the Taylor expansion for just h of x. If you remove this, then this is
There should be a constant.
like
part.
h.
Dude, I think this is because when you consider the fluctuations around the classical solution in the Gaussian integral, there's kind of a standard fluctuation that you get. I'm saying when you consider the fluctuations around the classical solution in the Gaussian integral, there's like a standard term that's going to appear that encodes the fluctuations, and that just must be this. I just can't remember how exactly you work it out, but I think it'll be easy to check.
Wait. What if we doing the fluctuation expansion of h prime of x and not h of x? Then that would explain the h double prime. That is the question, but there is a minus half. And that is coming from that minus outside and that half. Okay, so that's how it is. So it's not a Taylor expansion for h of x. It's a Taylor expansion for h prime of x. So this goes away.
Right.
This is, and then square of this is this thing. And this thing is 0. As we got.
Yeah, I think you're right. Yeah. Because h prime,
And that is h of x at x equals xi. But this is
that's
actually 0.
0. Yeah.
And that's how it's being squared. And this goes away. What happened?
Yeah, that final term is still
What about this one?
yeah, the explored by Vital definitely vanishes. That one,
But what
also,
else is it?
that also, that vanishes because we're only considering constants configurations. Yeah. Otherwise, these would be equal keys, right? These are, these are constants.
Okay, so there are no fluctuations
Yeah,
inside.
there's no time dependency.
Yeah, so that one goes away. Then the large term.
Yeah, that's yeah.
And those are the constant ones, the fluctuations that about which it's like not fluctuating, the constant ones. But then I don't know how to reconcile this with this one.
Well, it's the same as why we're integrating over x naughts.
But
General
just tell me
examples,
one thing,
right?
are psi and psi dagger independent?
Yeah. So we for the same reason that so x naught from here has to be xi.
Yeah.
But we're integrating over all the x naughts that aren't just equal to xi, but we're assuming that it's close enough to xi. So I suppose we're assuming, because we take it around xi.
Yeah.
So in some sense, we're saying, okay, we're considering variations that are close to the classical solution. Right? So that's why we take expand around where x and xi are close together. And in the same sense, I suppose we're considering fluctuations around 0. So phi, tag, phi.
But that is exactly 0. So in that sense, this would be 0. So this would be 0.
Yeah.
Right? So if that is 0, then this would be 0, no? And then we would get a 0 here and that's the.
This would be xi always. So considering phi's that are non-zero is the same as considering x naughts that are not equal to xi. You know what I mean? We're allowing for x naughts which fluctuate. What we are saying is that phi's and x's are constants, right?
Yeah.
That's how we're getting from a path integral to a normal integral.
But
Then we're allowing those
the
constants.
difference is psi and psi daggers are constant, but they are also 0.
Yeah.
X is a constant, but it could be any constant.
No, it couldn't. It has to be xi's. This is something
Wait. No, it can be any constant, But we know that due to the fluctuations and all that time, hence it has to be localized around xi, and we are summing over all that.
No, it's not due to any fluctuations in averages. This is an equation motion, just like this one is. This condition comes from the equation.
Yeah, okay.
This is as important as these two.
Okay.
So the x naught, from this one we get that as a constant.
Yeah.
And from this one we get that it has to be not any constant but xi, which is the root of h, which is known.
Okay.
Yeah.
Then you also get psi level is 0.
Yeah.
So where is it's not 0 here, it's a constant.
Yeah, just like x0 isn't xi. It's a constant. Same thing. That's what I'm saying. We're considering x naught to take values around that aren't necessarily xi but around xi.
Yeah.
Similarly, we're taking sides that aren't necessarily 0 but are around 0. That's why. Otherwise, this whole thing would be 0. If we were considering these exact solutions, this one would vanish and this one.
I got your what your logic about this, but I don't see why we are doing that here. Because we only got that expansion and that Gaussian thing on x. We didn't get any Gaussian thing and those things on sides. Right? This summation over I is only for x's.
Yeah.
Psi only depends on tau. It doesn't depend on x. Right?
Yeah. Well, it doesn't depend on how either, actually. It's just.
Yeah. In general, but still, like, why is there as we said that there's no fluctuation about like it's not a configuration anymore, it's fixed configuration.
Yeah. Yeah, I'm not sure. I just want to get coffee before
Yeah.
ratings. Did you write this thing down?
Yeah.
Let's look at it. Let's look at it later. Because this part actually.
Wait.
What?
For that, I missed that. I threw it and it landed there.
Oh, you got it. Because for the everything we find is in data functions, so that's not going to take notes of this section. This section does it.
that would actually look. Maybe it's a bit too small for it to come up. Picture might be come just a picture.
So, okay, so I'll take two pictures, one without the flash and one with the flash. Which are not primary, so.
Fully ready. Let's go ahead.
Yeah. It's blinking.
Yeah, it's blinking on this side.
And then you want to do the flash one.
Yeah.
Okay, thanks, Willie. And I think I'm ready with his potentially last.
Yeah, I think so, depending on how things go, I'm optimistic, but we'll see. So just a short recap of what we discussed in the last lecture. So we introduced this idea of Nielsen complexity. Nielsen complexity, where the idea was that you take the unitary gates from some symmetry. So all the unitary operations are from some symmetry group. And we showed a close connection between the measure of complexity in those the symmetry and the coherent state overlaps. And specifically, what you would have is a coherent state. So you would choose a different state, and you would act with an arbitrary element of this group. That's labeled by a set of real coordinates corresponding to the generators, and you get a coherent state. It's labeled by those same numbers. And what appeared in the FS metric was all the generators are not from the so-called stability subgroup. So you're ended up with a metric called the manifold G factoring out H, where H is the stability subgroup. It's a group of all the elements that act on the reference state in a trivial way. So either as an eigenvector or as always violates the reference state. And but we showed that from this, we focused on a specific example that was a Heisenberg group, and we show that you get the usual cloud coherent states out in this dimension. Now, another example that's slightly less trivial, but it's also well known, that I first want to focus on today is the block coherent states. And these are the coherent states corresponding to the group SU2. And in SU2, you have the JX, JY, JZ generators, and I'm just going to write it in the ladder operator basis. That's a bit simple for our case, but it doesn't really matter what mathematization you choose. Maybe plus minus, J plus minus, and J plus J minus gives you 2J0. So this is the algebra of generators. And what you now need to do is choose a reference state. And a very simple choice of reference state would be the spin J representation, the lowest order state. So it's this state J minus J. That has the properties that act with J0 on this, I'm going to get minus J. And it's annihilated by J minus. Right. And so in other words, these two generators are not going to feature on the manifold with coherent states. They're going to factor. And if you take any group element of SU2 and act on this reference state, what you're going to end up with is just the family of states e to the z, j plus j minus j, and then there'll be some normalization factor. And this is the set of coherent states. That's called the block coherent states. These will also find in the literature coherent states. That's called the block coherent states. These will also find in the literature. But the point here is just to illustrate that you can do this for any group. We've done this now for the Heisenberg group and SU2, but you can really do this for any group that you're interested in. Right. So, what we okay, so maybe just one other property that I think is useful to know about these coherent states. So let me do this for the case of the block coherent states and the Heisenberg coherent states. So just as a reminder, the Heisenberg coherent states were these e to the z and dagger if I choose the reference state to be the vacuum in this specific coherent states. One useful property of these is that I'm going to just also write down the corresponding algebra, A dagger, and right. Now, a useful feature of these coherent states is that the action of any of the algebra elements on these coherent states can be recast as a differential operator. So how does that work? Well, let's start with the Heisenberg coherent states, the reliable coherent states. If I take a dagger and act on this state Z, then that is the same as taking a derivative with respect to Z. So a dagger acting on Z is the same as acting with a derivative on the state in Z. Exactly the same state. And the action of A on this state, Z. Well, to get this, I need to make use of the algebra. So here I'm going to have A e to the Z a dagger given. And I can use the commutation relations to shift this A past the e to the Z a dagger. You can show that this is nothing other than A plus Z commutate from A with a dagger. And as you said, the value is annihilated by A, so this is the only term that remains, and I get Z times e to the Z. So A dagger acts as a derivative with respect to Z, and acting with A acts as a multiplication with Z. So this is an identity that I think you might have seen before, that the boundary unit states are, in a sense, eigenvectors of the annihilation operators or the properties. And you can play the same game for the SU2 algebra in this case. So, of course, if I act J plus, and we just call on the left-hand side in the state Z, if I act with J plus in the state Z, this is nothing other than a derivative with respect to Z. Let's say. Right. And J0, again, you can use these commutation relations. So you pull the exponential past it. This induces a commutators in this case. Now J0 plus Z, commutator of J0 J plus, acting on the vacuum state as J minus J. And now you can again use the transformation properties of this under these generators, and what you end up with is this is the same as acting minus J plus Z dz. Now, we can also get an expression for J minus. This I'll leave as another exercise. Here you're going to use two commutators for this sequence of commutations go to 0. But the final expression is 2z times J minus Z squared Z. So this is a useful property of these coherent states. That if I take something like the coherent state overlap and I want to compute expectation values of operators, I could use the fact that to generate one of these, to get one of these operators, I can take a probability derivatives with respect to Z and then compute it back. And this is quite relevant in the state that is now finally connecting back to the Nielsen complexity. So we've taken a bit of a detour into generalized coherent states, but ultimately what we want to compute is this key quantity that, so for a general coherent state, S1 prime, S2 prime, up to S prime, let's overlap with S1, S2, all that. So this function over here that I call curly K, this is the key quantity that we wanted to compute. By taking appropriate derivatives of the logarithm of this quantity we generated for the steady metric, and taking appropriate derivative, single derivative to the F1 cross function, for example. And there's a bunch of metrics that are related by taking appropriate derivatives or appropriate functions of this overlap. So this is the key quantity that we want to compute. So let's take the SU2 case, for example. It's slightly less trivial than the Heisenberg case. So what we want to compute is an overlap of the form J minus J e to the Z bar J minus e to the Z J plus e to J minus J. Now, I've got a normalization factor. This is because for the steady metric computation, at least, that normalization factor does not matter. It's not going to feature. It's not going to feature any sort of measure. So I've just talked about for conciseness. So now, how do we go about computing a quantity like this? So this is what we want to compute. In order to compute one of these things, the steady metric, one cross function. How can you go about doing this? Well, there are at least three methods that I'm aware of. So the first method is a bit of a brute force one, and just to do a series expansion of these exponentials. So you can write this as sum over n J minus J, and then you'll have Z bar J minus n factorial multiplied by Zj plus n factorial. This goes to and then you can use the transformation properties of the state on the J plus and J minus. So compute combinations, resum this and get a final answer. For general groups, this is going to be a very difficult thing to do because you're going to need to compete with a bunch of summations of these different generators. But this is not one that I would recommend. The second method is to make use of the identities that we've written down there in this sense. So what you can do is set up a differential equation for this one. So if I take a derivative with respect to Z of this, I'm just going to call this Z bar Z. If I take a derivative with respect to Z bar Z, What that is going to do is bring down, actually, we'll get to the bar as a bit more transparent. It's going to bring down the J minus. And the J minus, I can rewrite the differential operator in Z of this. So I can rewrite this dz bar of this quantity is the same as 2J Z minus Z squared dz. And we have the boundary condition that if I take 0Z, I should give you 1. That's a boundary condition. This is now a differential equation using those identities that we derived that sources this overlap. So this is another way to compute it that is quite efficient. And that works quite well. The third way is, in my opinion, the best way to go about this. It makes use of what are called Baker-Campbell-Hausdorff formulas. So what those are, well, we've already used one simple example of that yesterday with a Heisenberg, where if we have a combination of a Heisenberg group of t to the z bar a and t to the z a w, then we could rewrite this as a different ordering of these with, so we could have this as e to the z a w, e to the z bar a, with some factor over here, which if I recall correctly, yeah, e to the z bar. So you can recast it in this way. This is a Baker-Campbell-Hausdorff formula. The Baker-Campbell-Hausdorff formula in this case is very simple because A and A dagger commute to identity. So in general, you would have a bunch more commutators that you have to perform or compute in order to write up these identities of this type. But the point is that this is what you get. And why this is useful is if I now wedge this between the reference states. So on the right side, you've got e to the z a dagger. So an a dagger acts non-trivially on that vacuum. So it's going to raise it up to all the different non-operator states. And a is going to act on the graph in a similar way. But now that you solve them around, A acts trivially on the reference state. A dagger acts trivially on the reference graph. So this expression is nothing other than e to the z bar, which is just e to the z bar. So using the Baker-Campbell-Hausdorff formula, you can obtain this same overlap. If you use the differential operator method, you get exactly the same answer, but this is a very efficient way to go about doing this. But now, as I said, this is for a rather simple case in the Heisenberg algebra. How would you know about more general or more involved algebra, more involved group, to get similar sort of identities? So let's say that we want to take issue 2, for example, j minus j, e to the z minus j minus, e to the z j plus, j minus j. I want to compute this one here. Again, j plus acts non-trivially on the state, and j minus on the reference graph. And I want to recast this in a way where it's going to be the expectation value of some function times j plus, because that acts trivially on the reference graph, into the z j minus on the reference kent, and then it will be, as a spoiler, there's going to be some function of j0 appearing in the same interval. So how do I go about getting the identity of this form? Swapping these two exponentials or generators will take something like this. A very useful trick to use in this case is to just take any simple faithful representation of the algebra. This is an operator. So if I look at a faithful representation, you can write this identity with swap in a faithful representation, and into any other representation I wish. So the faithful representation of the SU2 algebra is in terms of the spin matrices, and 2 by 2 matrices. J plus, I can do J minus of 0, 0, and J0 of half, 0, 1. So, yeah, I've just picked a very simple faithful representation of an algebra, And now in this algebra, I can go about identifying the equivalent identity. So the first thing, of course, is to exponentiate. These generators with some coefficient z, which you can do either by hand or using something like Mathematica. But in this case, they turn out to be quite simple, so we can just do them by hand. So, using that representation for j plus, j minus, and j 0, you can get e to the z j plus. It's just going to be the matrix 1, z, 0, 1. And similarly, e to the z bar, j minus, which is going to be 1, z bar.
Sorry, Yaku. So the reason we're interested in this particular overlap is because this is the object that we can take various derivatives of to get the matrix.
Exactly. So the logarithm of that quantity is going to be the Taylor potential for the issue to complexity. Exactly. I should maybe add a comment here that actually came up in one of the discussion sessions yesterday on the lecture. So I won't get, so we know how to get the metric. To get the complexity, your job will not be done. What you'll have to do is compute the geodesics on that manifold, on that metric, and compute the geodesic distances between points. The geodesic distance is going to be the complexity. But certainly the first step is just to derive that metric. Here we're just using the VCH formulas to get an overlap, take the logarithm of that overlap, and then derivatives are going to give us the complexity of the metric. Yeah.
These methods are applicable only to covariance data, because we started from covariance data.
Yes, but with any group that you choose, any symmetry group, you will have associated coherent state. And even if you don't make this nice choice of reference states, this is in a sense the simplest choice of reference state, right? There's still an associated coherent state basis.
Well, and we are assuming that at daytime, we also preserve their basis.
So we haven't introduced any particular Hamiltonian into the system yet. So, so here we are essentially just interested in the relative complexity of the reference state with respect to some target state. And the target state in this case, the manifold is a coherent state, I'm assuming. But what's that? The coherent states give you a complete basis for the orbit space. So you can decompose any target state that you're interested into a linear combination of coherent states, and then complete the computation in that way. So that's why this is a sensible thing to install. Right. And lastly, into the lambda to 0. Well, it's just a diagonal matrix. So this is lambda to the minus lambda. So what we want to match up are the two sides of that operator identity. So we want to find function alpha and function lambda, and alpha bar minus, that is going to match up with e to the z bar minus e to the z j plus. We want to find this operator identity. We want to find the appropriate coefficients. Finding these coefficients comes down to solving the VCH form. So then it's a VCH formula, an operator identity for swapping these exponentials of the two generators. And with this faithful representation, we can now get the 2x2 matrix equation. So on the left-hand side, I get e to the lambda over 2 plus e to the minus lambda over 2 alpha of r. E to the minus lambda over 2 of r, e to the minus lambda over 2 alpha, and e to the minus lambda over 2. So this is the left hand side of the equation, and then on the right hand side, we obtain 1 z bar, 1 plus z bar. And now you may be worried that we've got 4 increase here in the coefficients. Both of these have determinant 1. So that's why it works out. So you still have your three independent equations to solve. And the solutions you get is alpha is equal to z over 1 plus z bar. And alpha bar is equal to z bar over 1 plus z bar. And the important one for us is that lambda is given by minus 2 log 1 plus z bar. This is the important one because when we reach this combination of exponentials between the lowest way reference state, then this is going to act trivially and this is going to act trivially on the graph respectively. It's only the center one that's going to give a contribution. And doing that, you can obtain so doing that, you can obtain for e to the z bar minus e to the z plus, which between the lowest weight instance j minus j, you can obtain j minus j. This will be e to the alpha j plus, this is not going to matter, e to the minus 2 log 1 plus z bar z, j0, e to the alpha bar minus j minus j. As I said, this acts trivially, j0 is, well, this is an eigenvector of j0 with eigenvalue minus j. So the final answer is 1 plus z bar to the power of 2j. This is the coherent step overlap formation. And if you solve those differential equations that you wrote on the right hand side of that boundary condition, we'll get exactly the same answer. So things are consistent. All right. So this is now the coherent state overlap, and just as a just to illustrate what we will do with this, to compute the Fibonacci symmetric, you take the logarithm of this. So your Taylor potential is going to be 2j logarithm of 1 plus z bar. And now you take the derivatives of this. So your g z bar is going to be given by 2j over 1 plus z bar squared. This, just watching this, I didn't actually write down the notes on this, but I think this is now the metric corresponding to the Nielsen complexity for EC2. Using the Fibonacci metric as your complexity metric. Now, this is not the full story, as I just mentioned. What you need to do now to compute the complexity is compute the geodesics of this geometry. So you solve the geodesic equation on this, and then put in the appropriate boundary conditions. Interested the boundary conditions meaning that the geodesic must go from the reference state to the target state of the one. Interested the boundary conditions meaning that the geodesic must go from the reference state to the target state of the one, and solve that equation for the boundary condition. And the geodesic distance is the complexity.
So how can we make sure that the complexity corresponds to zero?
Sorry, could you just make how the complexity?
How can we make sure that the complexity corresponds to zero?
Oh, so that's the way that it's defined in this case. So it's geodesic because you want. So remember that when we discussed the discrete case, we said that if there are multiple ways to get from your reference to target state, you choose the shortest, the lowest number of unit terms. In this language on the manifold, that means that's geodesic distance. So of course, to get from A to B, you can travel any path you like, but the geodesic distance is the one that will be the shortest between those two. And you can get instances where multiple geodesics. In fact, this is one of those examples because the geodesics. This is essentially the metric on the two-scale. And if you have a reference state in mind, then everywhere here there is then everywhere here there's one possible geodesic, and the other geodesic is around the other side. With a multiple, in this case, actually the target site. Those are your two possible geodesics. And the complexity is given by the shortest distance between those two. And this situation is also interesting because what's going to happen is that, say that I have a family of target states in mind, and this family of target states comes from, say, the time evolution of the state. What's going to happen is that, say that I have a family of target states in mind, and this family of target states comes from, say, the time evolution of the state. So I have some time evolved set of target states, time zero decided the reference state, then we want some of, and background on the side. The key thing is that as you evolve in time, the complexity is going to increase. So the geodesic distance on all these points are going to increase, probably increase linearly until they reach this point. When they reach this point, it's the other geodesic. It's going to matter. The complexity as a function of time in this case is going to seem small. So this is how we expect complexity time. So here you need a notion of a time evolved state. And I want the complexity of the time evolved state, and it's going to follow this way. This also links up with the sketch that we had yesterday for chaotic systems. What we wanted for chaotic systems was the complexity to increase up to a point and then plateau or halt. And this is only possible if conjugate points appear on this group. And in fact, in order for it to plateau like this, you do not one conjugate points, but many conjugate points in this case. So you need a large number of symmetry units in this case. If you are even not playing it using that one. So here you certainly reach a turning point, there's a single conjugate point, but it doesn't plateau at all. And that makes sense. If I take a Hamiltonian from the SU2 group, I expect it to be solvable integrals from that. So that is any case. And this is the sort of behavior that you can see.
So physically, in some system in which you're saying describes black holes, moving state, and so on, to construct this particular state from the vacuum requires roughly the same number of operations each time. Yeah, the suggestion working on some manifold where all the is equal length from any point to a reference point.
There's at least a confluence of geodesics, particularly on the manifold, so a large confluence of geodesics. So it may not be that every point is connected to another confluent internal geodesics, but you need to get a point where there's a confluence of geodesics. That's the idea at least.
Is there like a rate equation for the geodesics?
Oh, I'm not sure. That would be interesting. I don't know the answer to that. That would be very interesting to understand. Right. So, yeah, that does link up a bit with the next one I want to get to, and that is, well, we've studied this now in a simple example of SU2. You get the metric for 2 sphere. If you do the same for the Heisenberg, you'll get the flat space metric. If you do it for SU11, you'll get some hyperbolic geometry, very simple two-dimensional hyperbolic geometry. But one of the groups you might be interested in studying is the conformal due to its connection with a log. So SOP. And this is still an ongoing project. But let me just give the results of the work that sort of started these computations. And it's a paper by Shugnet, Blue, Chapman, and I forget the third author, unfortunately. But it's the title of the paper is a complexity for private general dimensions, something like that. It's one of the references I put on the web page. So the group you're interested in there is SMP2. And this is built from the generators of the conformal. So you've got ones corresponding to momentum, special conformal transformations, rotations, and scale. And of course, there's an algebraic structure associated with these. Well, I'm not going to go for just for time purposes, that's also not particularly important. We can already make large arguments just based on the action of these generators on the reference sets. We don't need all of that. So what you can do here is study, so the general group element, if I decompose it, so the general group element would be the exponential of some linear combination of these ones. You can split that up into separate exponentials. So you can have e to the I alpha of b, e to the I gamma times d, e to the I lambda mu L mu, and e to the I beta delta. So this dot product there are beta and alpha vectors, and there's d components. So it's a d component vector, and they are general complex numbers, like we have with these two lines of complex numbers. And in order to impose the unitarity condition on them, so in order to have unit equals 1, there's relations between these coefficients. So alpha and beta are independent from one another. Beta is determined in terms of the other ones. Again, it's not going to be too relevant for us. The reason it's not going to be too relevant is that the reference state that we choose is some scalar primary, state delta. This delta has the transformation properties that under the action of the computation operator take an eigenvalue, and it's annihilated by the special conformation. And in fact, in addition to that, they focus on primaries with atomic spin, so they're also annihilated by all the rotation derivatives. And with this choice of reference state, what we know from our study of generalized coherent states, well, these exponentials are not going to contribute, and we'll end up with the relevant coherent state in this case is just given by some normalization e to the I alpha dot. This is simple coherent states for the study, and these coherent states are a function of this choice of reference state. Now you could make a more general choice here, spinning a reference state, in which case there would be a non-trivial action of the rotation generators. This is also a computation that can be performed using the Camel Hausdorff formulas and you get an answer out of that. So let me just flash the metric of the compute. So the way that you go about this, again, you can do it in several ways. I think they use the differential operator approach in Python. So set up the differential operators for the variance and overlap. You can also do it using like a Camel Hausdorff formulas. A simple representation to use in that case is the defining representation of SOD-2, which is in terms of T plus two-dimensional matrices, if I recall correctly, and you can set up all the BCH formulas necessary for the computation. Nevertheless, I'm going to just skip over those details. Just know that the computational methods are virtually identical to what we do in those simple examples. And the metric that I obtain sigma squared given by 2 delta alpha prime. So alpha prime here means, remember that these are functions of sigma. So alpha prime is the derivative with respect to sigma. Alpha star prime star minus 2 alpha prime dot alpha squared and 1 minus 2 alpha dot star plus alpha star, and there's the second piece that's absolute value of alpha prime alpha star minus alpha star dot alpha star alpha dot prime squared over this factor 1 minus 2 alpha dot alpha star plus alpha dot star squared. So this is the metric that they obtain. They go about solving the geodesic equation. And the geodesics are actually parameterized pretty nicely in terms of the generators of the SOT2. The geodesics is simply given by e to the pi sigma p alpha some alpha tilde plus a p dot alpha tilde k dot star. These are the geodesics. What you have in mind is your circuit going from the state delta as your reference state and going to the state alpha. That's the circuit that you're describing, and this is the geodesic motion corresponding to that. You can compute the complexity in this case. The complexity and the compute is the complexity in this case. The complexity and the compute is I'm just showing the completeness. I don't know how much to say about this. Purposes. I'm just showing the completeness. I don't know how much to say about this. Purposes. Just showing you that this can be done. Orbital is not. Just showing you that this can be done. Orbital is not. This is a complexity associated with these points. The important bit of information I want to give here is that there are no conjugate bonds, period bonds. And it's quite easy to understand why. What you've included in this case are just non-compact generators, the keys. They give rise to a manifold of constant negative scalar curvature. Because of that, there's no points where the geodesics can swap around. There's a single geodesic in this case. One way that you might hope to remedy this is by studying more involved sources of reference state, one that have spin, because the spin generators are compact. So you can expect to perhaps see conjugate points there. And I know that metric has been computed for the spinning case. Conjugate points have not yet been shown there, so that is still an outstanding piece of work, but this is done here. These are the results that you obtain, and certainly working with just these generators is not enough to see any conjugate points. Are there any questions at this stage for the Nielsen complexity? So what I want to do in the last section is introduce briefly another notion of complexity that has seen some popularity in the literature for few events, which is Kuhn complexity. So to put together the calculations for Nielsen complexity, we have to make several choices. So you have to choose the reference state group, you have to make a choice of a reference state, you have to make a choice of metric on this space. So there's a lot of ambiguity built into these definitions. On top of that, what you can expect to simulate chaotic dynamics is an enormous number of symmetry generators. And it's not clear that the computations will be tractable in those cases. So there is another notion of complexity that has seen some popularity because it's based the.
So, just a question.
Sure.
Just speaking of what you just said, has this sort of thing been done for, say, Gregor algebra or log function generators?
Yes, I believe so. I believe that's been on the as well. Yeah, absolutely. So I'm trying to think if it was, I think it was two-dimensional drizzle. So yeah, exactly. That has been done. But the computation is a little bit different in the sense that you, it's slightly different to what I was saying here, but it can be done. They're more similar models. You have some unitaries in the different state. You can move on a metric, from corporate, the metric that uses a little bit different, but the same idea is the one. Yeah.
So are you asking basically what is this working done for an three-dimensional algebra or for basically I was thinking more specifically there as well, because oftentimes a lot of black hole counting using GPCFPs.
hierarchical complexity. There was a paper in 1918 by Ivansky. They completed it, but there was some error in their paper. And then there was another paper later on by the group at BBC. They pointed out how to do it for this.
So the notion of complexity that I just want to introduce briefly in the last bit is kernel complexity. And one of the beauties of kernel complexity is it doesn't rely on a lot of these choices in order to obtain answers, so to quantify complexity. Really, the only two choices you need to make is the choice of Hamiltonian and the choice of reference state. So what is the reference state that you're solving for? What's the zero complexity state? With these two definitions, the starting point is looking at the time evolved state. So time evolved state is equal to the I to H and the reference states. And the idea is now to look at the powers of H acting on the reference state. So I can expand this on course of the power series. I teach somewhere in H to the power of and the idea is that this is now a basis in which you can do your complexity calculations. So you start off with the basis H to the power of n and the sum. Now, these states are not necessarily your fault. So what we want to do is first formalize this. There are several ways to do this, but one popular way is the so-called matrix algorithm that does this in a recursive way. But ultimately, all that you want to do is compute this, do the Gram-Schmidt process. Obtain a basis, it's called the Krugel basis. Right. So once you have this basis, the way to now compute the complexity of the state is to take the expectation value of the operator sum of n times k in n times k in And the intuition behind this is that you have two operations at your disposal. I think this picture is correct. The gate complexity advantage. You have two operations at your disposal. One is time evolution, and the other is like superpositions of states. You have those two operations at your disposal, and the more complex states are ones that you had to wait for a long time to obtain. So those are the ones that generate only at high orders in which the and these are the more complex states. And you weight those with a weight of n. So ones that are high powers of H, you expect to be more complex in this case. Now, there's a very nice proof that was put forward by Paul Buch and his collaborators, but they said, well, is there another way to motivate this choice of complexity operator? Look at is, let's choose a different basis, not necessarily a different basis, but that has this ordered structure that K0, I'm going to give complexity of 0, K1 a complexity of 1, K2 a complexity of 2, and so on. If I consider any ordered basis, so let's call this B0, B1, all the way up to the end. And I construct a similar operator like this, and I minimize the all choices of basis, minimizing the basis of the expectation value of your time evolved state being as a time evolved state, minimize it with the choices of B. The choice that minimizes that sum is exactly the critical basis. So in that sense, it's the in the space of all choices of basis, it is the minimal choice. So that's why it's really big enough. This is the critical basis.
Yeah, I just want to make sure the critical basis here is obtained using Hamiltonian, not the Lewis.
So for the purposes of our discussion, we're thinking of state, or state completeness. So in this case, it would be the system alternative. Yes, that's right. That's correct.
So you didn't say, this is actually calculable in the sense that, you know, the lots and lots of choices of basis. So how would you scan over all the possibilities to find the actual limit?
Oh, so I think the argument that was made by Pavel and his collaborators was quite a different one. So you assume that the kernel basis is the number one. And then for the next basis vector that you're including, you're now asking, well, what if it's, I forget the details very often, but it can be that way. So you don't scan over all possible choices of basis. You just, I think it was shown that if you take the kernel basis plus any of the other basis vector, you get a bigger answer in that case. But all the argument of the correction in that case. So this is the definition of kernel complexity. Well, I just put a flash in the last part of this lecture, just how coherent states can again be used to do explicit computations. So this is still a newer notion of complexity, at least in the state case of quantum states. But coherent states seem to play an important role. It seems in general. And certainly for the simple cases, such as issue 2, Heisenberg issue 1, the problem can be solved completely. So let's take issue 2 as the example that we introduced before, and just look at the pure complexity. So let's pick a Hamiltonian from the issue 2 algebra. So this will be anything of the form alpha j plus alpha mod minus plus gamma j0. And we'll again choose as our reference state the lowest weight reference state, J minus. Right. Now, let's just work through the first few orders of this using this. Let's just see what the action of H on this state is going to do. So if I have H1s on this reference state, J minus J, that's going to be annihilated by J minus. That's going to have an vector with J0, so I'm going to get minus J gamma J minus J. And J plus is going to act on J. So we're going to get plus J plus acting on J minus J. And we'll go to But before looking at the next order, let's just formalize this already. So I've already seen this vector at the next order before. So the imperial basis K1 is going to be this one over here. Alpha J plus J minus J. I've already seen the reference state before, 0 order is computation. So the orthogonal choices that are. What happens now at the next order? Well, at the next order, H squared on this. So again, J0 is going to act diagonally. So I'm going to get, I'm going to get something from here. J0 acting on this, so I'm going to get some number times J minus J. Then I'm going to get a different number of J plus acting on J minus J. And then the other option is, of course, to act with J plus twice, plus alpha squared J plus. And again, this one I've seen at the 0th order. This one I've seen at the first order. So the kernel vector in this case, the second order one, is just alpha squared J plus squared. And so on. In fact, at the nth order, you're going to have n actions of J plus, There's going to be sample normalization, J plus n times the reference state. Okay. And of course, in the issue 2 case, this is going to terminate at some point. So it's going to terminate after I've applied its 2 times. I get a finite dimensional kernel basis in this case. If you were working with something like a Heisenberg group, this would continue going to infinity. But in the case of issue 2, it terminates at some point. So the quantity, so in other words, what you can see here is that we can order the kernel basis in terms of the coherent states. Because the coherent states for issue 2 are e to the zj plus acting on j minus j. So the nth order in Z of this is going to give me exactly the Krylov basis vector. So in derivatives with respect to Z, it's going to give me the Krylov basis vector of the normalization in this case. And what that means for the Krylov complexity is that what that means for the Krylov complexity in this case. So the Krylov complexity operator, so this is a quantity that I want to take its expectation value of in the time of the state in order to get the complexity. So I'm going to have J plus the power of n acts on the reference state, J minus J. And here I have the mission conjugate, which is going to be J minus to the power of n. Over, then we need to normalize this. So we need to normalize these vectors, and the normalization factor is going to be J minus J. J minus to the power of n, J plus J minus J. Sum in times n. This is the Krylov complexity operator. And if I have a particular state in mind, so say I want to compute the complexity of the state Z. This is effective because the time of state is not to H acting on the reference state. You can recast this as a coherent state. So there's a parameterization of Z as a function of time, will give you exactly that state. And you can show this using MDC examples, but they have a high before. This is a linear combination of J0, J plus, J minus. I can decompose those to get there's going to be some function of Z, a function of time, J plus, acting on the reference state, and that's that function that's So I see it as almost in class, so I'm just going to wrap up this is a final exercise. To show that in this case, if I want the coherence, if I want the expectation value of this with respect to some coherent state, so what I need to do is compute simply ZPZ. ZPZ of the normal quantities. There's going to be a normalization of ZPZ of the log of this quantity is exactly Krylov complexity for that coherent state. And you can do this by just plugging this into an expectation value of perspective this coherent state Z. Just show that these two. So it seems that coherent states also play an important role in computations of Krylov complexity. Of course, we've chosen a very simple example of this. Choose more involved Hamiltonians coming from bigger symmetry groups. For formalization procedures likely to be much more involved and combinatorial associated with much more involved. There's good evidence to suspect that coherent states again play a key role in performing those computations. That gives you a sensible conclusion. Any question?
What you are developing Krylov complexity in terms of There's another modality that we need to about, in terms of supercomputing operator. That's not very common. Operator.
Yes, that's right. Not work for the operator. Exactly. Yeah.
So, I think that
I believe that it's a bit hard to say because it's a bit hard to say that I suspect they are. Yes, I suspect that the group of operators for the circular grounding system will be the same as the group of states. So because of operators, you don't use powers of H for commuters of H with your initial choice of operators. You can think of a spin chain, for example. You start with localized excitation and subsequent commutators with the billion is going to hold up more complex states involving all the sites in the spin chain. I suspect that those two are equivalent, but I'm not sure.
If I may just add to this, this may be like not necessarily true because we know of some charismatic systems where there are star states, right? And these are the states that are like weakly DTH value. So if you calculate complexity for, or let's say pillar complexity or spread complexity for these states, then it won't grow as fast as the other states, right? So the operator complexity and this complexity may not be necessary.
So I think one needs to certainly a caveat there. Right? I think it's in a sense similar to what we had with our discussion on classical trade-offs, where you can have special choices of initial conditions that both will trade. And it's more a question of what's the generic initial condition going to do. So you need a way to identify a generic operator or generic state in the system and ask how that is going to evolve. So, but there can certainly be exceptions, even if there are systems.
I also have another question. So we calculated using coding basis Nielsen complexity.
Yes, that's right.
Like I don't recall the formula for Nielsen complexity right now, but this formula and that one look pretty similar.
They're all similar. It's not that you don't obtain the same cost because for the those complexity two different things. But the point is that the coherent state overlap, the logarithm of that is it still sources. In that case, it sources the metric flow. So your job is not done in the complex of the complexity. It's still in the computer to release the system. But the coherent state overlap seems to play a key role. For Nielsen complexity, I can state that that's always the case, that the coherent state plays a central role. Compute those Nielsen complexity. For Creole complexity, it's clear that this is the case certainly in the simple involvement. So let me just maybe explore that a little. The reason this example is particularly simple is that you have a single lambda operator, op ladder acting on the lowest weight state. If you were to have multiple ladder operators, then the action of these multiple ladder operators are to formalize them. It's not clear that this has a nice representation of the states, but there will be some representation. But a formula like that, I don't expect to survive. I expect there'll be something more involved.
Okay, then let's thank the applicant for this. And I believe that will be around, maybe tomorrow should might be.
So I'm not going to be here tomorrow morning. I will be here.
So everybody has more things to discuss about these. And last thing, should be ready to again, can unlock the.
It's all two. So
The last year's talking about it.
we will
But it
just that's
yeah.
so I think that's so I think it's not too similar to issue one. It's similar to issue each you want to mark. So you can generate the combined.
And the basic is also like
Let's say it's given to us.
but in case there in a product, so the initial value is they show that if you use the correct product, then
So in this case, you can again choose the that's a pilot
yeah, and that's what we see. Yeah, that's what this, even though they can try to see the for individual, it was saturated net whatever it was going information. But this another big thing is that the inner product was incorrect. Inner product this is the zero basically working in some sectors of which
aspects for this choice of sound. So in this case is that you could give it state over so
it's not
yeah, so with the issue two sphere, this is something.
What is the difference of the two, complexity designation?
Oh,
Right, the shortest one is what you define.
yeah, that's, I think that is you could apply both computations. So you will given that state, you will not take a target state. And you can obtain it in this optimal way and the suboptimal way.
Right.
So in a way that will quantify the work that you need to do to complete that final state. And the one would just be the suboptimal amount of work, and the complexity would be the optimal amount of work to get that state. Exactly.
And with the, sorry,
Sure.
I was minimizing the spaces. I'm wondering, what if you were to take the, to prove that it's the minimum? Wouldn't it be sufficient that to make the basis any smaller than whatever the dimension of the number of came in?
Yes.
Nobody has one when I see the state.
One of the things that.
That's right.
I'm going to catch him before he goes to
The equivalent basis.
Yes, so
Yeah.
Like reducing any smaller than the equivalent form, equivalent,
say Krillon?
equivalent basis. Any, making it any smaller than that, it is not.
So you make so what is that we have here? So say that you have a vulnerable state, and now it's going to be, let's say that we're going to T, you're going to have H. H. Give you a minute. That's not too much. What is that? So this is just identically this is some weighting of K1 and some combination of K0, some number. And this one is going to be obviously some combination of K0 K1. And what is that? You've already accounted for K0 and K1. This is zero complexity that is contributing K1 that is contributing a single unit of complexity. And now you want to minimize This bit that you have here, well, it's some combination of things. So I know that this is the best choice one can make for the first one, because any other choice that includes, say, another choice for the subspace is going to be A0 and some non-limit choice, right? So this is another choice that you can make. Ideally, you're going to add more of N1, so more units of complexity. So that's one of the things here. It's an argument that goes something.